Thank you, Marco, and thank you, Aspetar, for giving me the opportunity to come and talk tonight on something that I've been doing for almost 30 years now. I know I look quite young, but there's a lot of years behind this face. Yes, jumping. As Marco said, I've been working with jumpers, the British long and triple jump squads, high jumpers, since 1992, before coming to Qatar almost 8 years ago. And what I'm going to talk to you tonight is a bit of an overview of the application of jump assessment. It's more born out of experience than a historical approach and looking to past research. Hopefully there'll be some take-home messages for you, particularly around force plate assessments, which have become quite frequent in the literature these days. So why do we test jumpers' ability? As I said, it's nothing new. We've been testing jumps. Bosco's work back in the 80s did a lot of work on jump testing, and I dare say jump testing was happening long before that. One of the reasons why I'm not going to quote too many research papers is that a lot of this boils down to Newton's laws and conservation of energy, as J.B. Morin just said in his talk. But ultimately, what we're trying to do, we're trying to measure an athlete's ability to accelerate their body by applying force rapidly against the ground in a very controlled, easy to measure and reliable test. And the different applications of jump testing are the following: identifying talent, profiling athletes' physical or physiological attributes, tracking changes before and after training phases, detecting asymmetries in muscle output from a return to play scenario, and detecting how athletes are responding to training loads in fatigue monitoring, which has become quite an in vogue new type of assessment of jumps in currently. So common jump types. This is a squat jump. You see they start in a squat position, and it's essentially a measure of concentric muscle output. Another one is a counter movement, where you start in an upright position, you bend down, initiating a low velocity stretch shortening cycle, which is essentially eccentric followed by concentric. Then we move on to a more demanding jump, which is a drop jump. It's an impact response stretch shortening cycle with an eccentric concentric phase. But we mustn't forget that there are other types of jumps in a horizontal direction, like the standing long jump. And again, like the counter movement, it's a self-initiated stretch shortening cycle with no impact, this time for distance. So there's many options for assessing jumping ability. They range from very cheap to very expensive, and it all depends on the amount of information and the depth of information you want. So chalk and wall, very simple, costs about £1. A Vertec, a little bit more expensive because you've got some equipment there, ranging probably from £1 to about £100. I'm talking in pounds because I'm British. These measure jump height only. Then we've got systems like contact mats and light beams. They measure flight time and contact time and use a formula G times flight time squared over 8 to measure jump height. They range from £10 to about £1,000, and they also give you some other time-based variables like reactive strength index. JB mentioned an app, smartphone app. This one's called MyJump. That will use flight time and accelerometer and the video input, and will also give you force velocity profiles. Very cheap application as well. Then we go on to force platforms. They give you force-derived measures and can range from about £1,000 up to £15,000. But they give you the added information of much more in-depth analysis of forces, power, velocity, asymmetries, and movement strategies that I'll talk about in a minute or two. This is the squat jump, and what we can see here is a force trace, and we start with body weight, and we can detect the onset of movement here. It's very critical to get a good measure of body weight and a very stable force at the beginning. Otherwise, it affects the onset of integration and the calculations of onset of the movement. So steady body weight is absolutely critical. So we see Mustafa there in a squat position. Everything is concentric. He jumps up, pushes hard, he's going for maximal height, and then he lands again. So what we've got here, we've got some characteristic markers on the force trace, which tells us the start of movement, the peak takeoff force, takeoff, landing, and from that we can get things like movement time, flight time, and the displacement graph is calculated from the impulse displacement methods, and we can see that the net change in height from the point of takeoff to the maximum displacement gives us our jump height. The counter movement jump, again, important for a stable body weight at the beginning. We start upright, we bend down, stretch, shorten, cycle, explosive off the ground. We've got a flight and a landing. Characteristic points, movement time can now be split into eccentric time and concentric time. We've got our flight time, our displacement graph, and the net change in displacement gives us our jump height. The drop jump, we land with 2 feet at the same time. We accept the force, we drive off, and we go for maximum height. This is a lot more challenging, as you can see from the impact. And the things we get from here are contact time, eccentric time, concentric time, flight time. Again, displacement and jump height. But with the drop jump, we also get other measures like reactive strength index, which is flight time over contact time. That's basically saying how much more time can I spend in the air than I did on the ground, generating the impulse to get the height that they achieve. And another one that's quite in vogue at the minute is vertical stiffness, which is a measure of the peak force in the contact phase divided by the maximum displacement in the contact as well. But I'm going to focus more on the counter movement jump because there's a lot of research now on counter movement jump and its different applications. And if I'm honest with you, sometimes I get a little bit confused by the different terminology. So what I'm going to try and do is explain the terminology to you and show you how that all relates to jump performance. So we measure displacement from the onset position. Here in a counter movement jump, you're upright. In a squat jump, you're much lower, but that would be your reference point. We start bending down, we get to the maximum descent, and at the maximum descent, you can see that the peak force here is very close to the onset of the concentric phase. Some people mistakenly think that the bottom here in the trough is the end of eccentric phase, but it's not. If we look at the displacement graph, we can see it's at the lowest point is when you're close to your peak force. We then push up to the point of takeoff, and you can see that this is the displacement of the center of mass. Again, we look at the displacement at the point of takeoff, the maximum displacement, and jump height is the difference between the two. If we can just slide that down now, it overlays onto the displacement curve, and we can see that the maximum displacement here, the depth of the counter movement, is also when velocity is 0. So we start with 0 velocity. At the end of the displacement, at the onset of the concentric phase, velocity is 0 as well. We can pick out things like peak eccentric velocity, how quick you are in the counter movement, and the peak concentric velocity. But the jump height is the effect of the impulse, the area or the net area under the force time curve. So we're going to look at that in a bit more detail now. So the velocity of takeoff we can also calculate the jump height from that using conservation of energy. It works out as the velocity of takeoff squared divided by 2 times gravitational acceleration. This part of the graph, from the onset of movement to where we re-establish body weight, is called eccentric unloading impulse. From that point where we re-establish body weight to the point of the concentric phase is called eccentric deceleration impulse. And because velocity is 0 at both points, then that means that these two areas are the same. It also means that the concentric phase governs how high we jump. Okay, so here we've got the concentric active impulse, the area above body weight, and then we have a little bit of unloading impulse, and it's the net concentric impulse that gives us the mass times the velocity at takeoff. This is another variable that we threw into some of our software, which we call the positive takeoff impulse, and that's essentially the muscular effort in eccentric and concentric phases before any unloading. So let's look at movement strategies. We hear a lot about movement strategies now, particularly in terms of neural fatigue and how people achieve a jump performance. So we've just said before, jump height is determined by the net impulse in the concentric phase. But the force at the onset of the concentric phase is a consequence of the eccentric phase. And I just want to demonstrate something here. If the eccentric phase was slower and longer, so it's longer duration, slower and deeper, what that would effectively give us is a longer eccentric phase and a slower rate of force development leading up to the end of the eccentric phase. So the force at the onset of concentric phase, it's often referred to as force at 0 velocity as well, is a lot lower. Now bearing in mind that the force at the onset of concentric phase in a squat jump is your body weight, the effect of the counter movement is raising the tension within your system to a much higher level than body weight. But the effect of a slower and deeper eccentric phase is meaning that the onset of your concentric phase, the force is not as high. Now by virtue of being lower and not having as much force at the onset of concentric phase, means that your concentric time will be longer. But that's not to say that the jump height will be any less, or it could be the same. If you've got the same jump height, there will be a performance deficit by virtue that it takes you longer to achieve the same result. So what we're looking for some really finely tuned athlete is that you generate more concentric impulse in a shorter duration. So the latest application of force plate technology really has been in neuromuscular fatigue monitoring. That is a term that I struggle to understand at times, but I'll try and put some sense around it now. Some individuals go for the golden bullet variable, like force and onset of concentric phase. For me, I think there's more to it than that. I think it's a process. And we have to create athlete-specific thresholds of when they're fresh. So when they're rested after 2 days or more, you start taking data and building up that profile and threshold of what fresh looks like. Some people would say that jump height isn't sensitive to neuromuscular fatigue monitoring. Now I would say that's your context. Your jump height is your performance outcome. If you don't use that first, then you're missing part of the story. You've got to look at jump height. And this is the workflow that I would go through. If my performance, my jump height, is greater than the upper threshold, I would say that the athlete would be fairly fresh. If they're lower than the threshold, I'd say they're fatigued. I'm trying to make this as much common sense as I can. But if they're in the middle of this threshold, we would probably need to explore it further. And by looking at it in more depth, I'm now going to look at the concentric time and my force at the onset of the concentric phase. So if my concentric time or the force at the onset of the concentric phase is the same or better, I would probably say the athlete is recovered. If the concentric time is longer or the force at the onset of concentric phase is lower, there could be some performance deficit. Now, because this is one performance, everything is interrelated. I think we lose sight of that at times. So if I've got a longer concentric time, just going back on what I said before, it will be a deeper counter movement, slower. You will also get a lower peak eccentric velocity, lower eccentric rate of force development, and a deeper counter movement. So what? Okay, that's a question. So what, when you're working in an integrated support team, what does this mean? And what interventions do you do from it? So if an athlete is spending a little bit more time in the concentric phase, maybe not jumping quite as high, it would indicate that they're using more muscular effort than using the elastic tissue, so it becomes less efficient. It also may point out that one leg isn't functioning as well. So therefore, the interventions could be, and I'm not saying this is for definite, but they could be. If you've got signs of fatigue, you've got to be looking at conversations around recovery. If you've got some asymmetry, or one leg is not functioning, then we do some musculoskeletal assessment, look at the asymmetry of left and right forces, which a lot of the force plate systems now give you. This is now an example of a test we do with some of our jumpers at Aspire. It's quite unique. We're doing a test called the 1-1. And young jabber here, he starts with a counter movement. He jumps up as high as he can. He's going over 50 centimetres there. He lands and he tries to get out of that as quick as he can to do a rebound jump. So everything in this test is about responding to his maximal effort. So we've plotted Jabber over time all season, and we can see our thresholds. This is his average on a Sunday when he's rested, and we do Sunday and Thursday. Our weekends here are Friday, Saturday. So we have thresholds of on the green line of the upper threshold, and the red line is the lower threshold. We're looking to see when he's in the above the upper threshold and when he's below. Here we would say he would be showing signs of fatigue. For the reactive part, we can use many different variables from coefficient of restitution, which I've got here, which is an indication of the ratio between velocity impact to the velocity out. We could look at other things like stiffness. We can look at reactive strength index, various measures. But what it does, we've got a little indicator here, and what we don't want to be is in the red. Ideally we want to be in the green here, where he's jumping as high as he can above the upper threshold, and is responding to that very well as well. But we don't want to see is in the red here, where he's not jumping as high as he can, and even if he's not jumping as high, if he can't respond to that. So we're looking at explosiveness in the counter movement and reactiveness in the drop jump part of it. But, and this is a real big but, these are observations to support decisions, not necessarily to make decisions in isolation. I think we can often lose sight that the data we collect is the be-all and end-all, and it's not. We've got to look at these results in the context of the overall holistic athlete profile, the stage that they're in their training program, what their performance goals are. We need to listen to the athlete's feedback and then telling us if they're tired or not. And coaches and other support staff intelligence on the boys. So it's putting the icing on the cake, if you like. The quantitative information from the jump testing is supporting the overall picture. Return to play is another area that the physios are very keen to look at. Here we can see a force profile of someone who's very heavily right leg dominant, possibly post-injury. We can see big deficits biased towards the right leg based on peak force, which are these values here, the average in the eccentric phase and the average in the concentric phase. These are very simple measures of what that graph is showing us. But how do we interpret that? A lot of people just go 10% difference and that'll do them. Well, what we did, we looked at thresholds. Again, we looked at the absolute difference between two limbs. We're not looking at dominant, non-dominant, we're just saying what would be a typical difference between two limbs. We found the average, absolute difference and standard deviation, and our threshold was absolute difference, mean, plus a standard deviation. And what we see here are for different sports, cricket, rugby, soccer, and some elite athletes as well, these were the typical thresholds. Beyond those thresholds, I'd be pretty inclined to say there is some asymmetry there that the physios and the S&C coaches and the coaches may want to look into further. But interestingly, in this data, what we can see is that soccer players tended to be a little bit more symmetrical than the other players. Now, there could be some reasons for that. Some sports predispose participants to some asymmetrical movements. So this is why it's important to look at sport-specific thresholds of asymmetry to try and make some intelligence and some decisions from that information. This is my final slide, and just to put performance in context, this is a grading scheme that we've got for our boys at Aspire. It's derived from almost 30 years of testing jumps, long and triple jumping in particular, acknowledging that performance is just not about jumping. It's about speed, it's about strength, power, the reactiveness against the ground, and how they put that into a horizontal jump performance. And what we see is, when our boys entered our program at the age of 15, we're looking for jump heights of around 33 centimetres. And interestingly, their drop jump performance from 40 centimetre drop height is 29 centimetres with a reactivity of 1.45. These are just some simple metrics that we extract. We don't go to the full depth of force at onset of concentric phase, etc. We keep it very simple. By the time they leave the academy, if they were world junior potential, we would expect jump height in the counter movement of about 57 centimetres, 56 centimetres in the drop jump. That gap has got smaller. Reactivity index of 3.43 and a contact time of around about 0.2 of a second. If you look a little bit higher, senior athletes, world-class athletes, your Mutaz Barshims, your Jonathan Edwards, these sort of guys would be doing 65 centimetres plus in the counter movement jump and the drop jump the same. Anecdotally, what we see as our athletes get older, their drop jump performance, their ability to react matches that of the counter movement jump. The deficit between them decreases. So, and again, the senior athletes will be spending over 4 times more time in the air than they would do in the contact as well. So hopefully that's given you a bit of an insight into what is a good jump performance, the different applications of jump testing, and that's me done. Thank you very much.